So I want to start with the big, I guess the biggest picture of all is what are the plans? The plans are today to derive the Maxwell equations and the stuff on this t-shirt. Tomorrow we're going to do Quaternion quantum mechanics demystified. So a bunch of those issues that you feel like, why does this work? Well, I feel like I've taken a step closer to appreciating it. It doesn't make it easy. It still started hard as hell. But I think you might make a step forward, which is cool. And then Saturday is going to be about Quaternion animations. It's my belief that someday, this book by Jackson, where was Jackson? David Jackson. Every equation in this might just have an animation. That's a dream. That's a big dream. It's easy to define, right? Okay, so I go to this place and I click on it and I get a picture. But it's my belief that someday that might happen, which would be amazing. Because otherwise these are rather hard to read. All right. Okay, so let me give you the big why for me of this project. And that is that I am not a standard physicist. I don't work as a physicist. I am a lunchbox physicist. And by lunchbox, I mean, this is literally my lunchbox. I use it every single day. So this is something that I do for fun in my slivers of free time, because I have a full-time job, a full-time wife, a full-time 2-year-old, and it's only from 10 p.m. to 1 or 2 that I actually get to work on this. And the reason is on the box, okay? And so let me read this to you. This is from John Archibald Wheeler, who wrote this nice thick book along with Thorne Wheeler. Misner. He said, "How can physics live up to its true greatness except by a new revolution in outlook, which dwarfs all past revolutions? And when it comes, won't we say to each other, quote, 'Oh, how beautiful and simple it all is. How could we have missed it for so long?'" What's so cool and powerful about that is this guy wrote a phone book of a book that if you ever, get to read it, is like not simple. Okay? It is not simple. So what is my proposal? Well, Newton said that time is absolute and space is absolute. He wasn't actually happy with that as an answer. But his mathematics compelled him to say that, and so he went with his math. In 1905, Einstein figured out how, for people who were moving at a nice constant velocity, time and space could rotate into one another. And that was special relativity. And then working with the smartest math guys around, because he wasn't so good at math and he could use them help, he figured out in 1915 how to generalize this. You could be on some kind of crazy surfboard and you could still agree to what was going on. But the math was so hard then that they could only solve a few very simple situations. We go 80, 90 years later, the math is still hard. You make global news if you find a new answer, okay? And it's just not very easy. What I'm going to do is I'm going to put time next to space. I am never going to let them separate. It's kind of like putting them together, putting them in bed together and saying, you have to stay in bed together. There is no operation that I will allow that allows you to think of time separate from space. This is kind of an odd fetish, but you'll see that I use it consistently throughout. Okay? So that is my goal, to put time right next to space, never break that rule, and see all the consequences that happen, and I think some of them are very cool. All right, so the focus of today's talk is trying to find a meaning in this very t-shirt, which you are going to do the work. You're going to earn this t-shirt, okay? You're going to have to go through all this now. And visually, what we're doing here is saying that the math that's on the back, which is really rather scary, somehow implies all the big claims on the front. Okay. So let's go over the big claims on the front. The stand-up physicist said a math equation, and there was light, gravity, radiation, and a nucleus, but no stinking Higgs. Visualphysics.org. And on the back, there are very few words. There's this one symbol that maybe some of you aren't familiar with. It's called a Lagrangian. So one Lagrangian to rule them all. J.R.R. Albert Tolkien. No, there was no J.R. Something about hypercomplex and quaternion products. All right, so now we're going to parse what it said on the front. And we're going to look at the stand-up physicist, this light gravity radiation and nucleus, the no stinking Higgs comment, and visualphysics.org. So who is a stand-up physicist? What has he done? He's got a secret identity. We may never know who he is. But he's got over 100 YouTube videos up there, medium to really long talks. And the reason I claim to be the stand-up physicist, I just let it slip, was that I do a short skit at the end as a reward for going through that much hardcore math. And all you have to do is leave a lot of downloads up for years, and you can end up with 150,000 downloads. But I like to think of it as global outreach to non-professional folks. All right. So then it talks about these light gravity radiation and the nucleus. Those are the 4 known fundamental forces of nature. Light and gravity, I think, are pretty familiar to everybody who's sitting down in this room. The weak force gets less press. It has to do with a particular form of radiation decay, beta decay. It only works over a limited range. The strong force is something that keeps a nucleus together. So that's very, very important. It uses gluons, and those travel at the speed of light, but because of confinement they go, but I don't want to leave the room of the nucleus. That's something called confinement. All right. Now it says no stinking Higgs. This is a variation on a quote, no stinking badges, which was made famous in a Bogart movie. Let's see if we get our amp working here.
We don't need no badges. I don't have to show you any stinking badges.
They're not funny closer.
No seas tonto, hombre. We ain't trying to do you any harm. Why don't you try to be a little more polite? Give us your gun, and we leave you in peace.
I need my gun myself.
Oh, throw that old iron over here. We'll pick it up and go on our way.
You go anywhere without my gun and go quick.
So that's where that phrase comes from. So the Higgs particle, there's a $10 billion search going on for the Higgs boson at the Large Hadron Collider. This is a little bit misleading in the sense that they've been looking for the Higgs boson for like 20 years. Okay, so they're just putting another $10 billion into the till. And it's that thing that's called the God particle. A little story behind that. The physicist who proposed that actually wanted to call the book the goddamn particle. Because he was frustrated at not finding it. This was like 10 years ago, okay? And on top of that, and so his editor said, yeah, but it will sell a lot more books if we just shortened it to the God particle. So that was not an act of arrogance, which I think is important. It was an act actually of frustration, modified to sell a lot of books. Okay, so what the Higgs does is it's one essential way of giving mass to particles. And it has to do a trick. It's got to be able to break symmetry without breaking symmetry. There are symmetries in there that if they're broken, then you'd say, this isn't conserved anymore. If you break U1 symmetry, the symmetry underlying electricity, then you'd say electric charge isn't conserved anymore. And there are some people, experimentalists, that say, well, we know it's conserved out to 40 decimal places. So you better not break it. That would be very bad. And the Higgs mechanism somehow has that ability to do that. And what this T-shirt actually argues, actually at this point, well, actually I'll get there, is that the Higgs mechanism isn't needed. All right, that's right. I should turn on my battery-powered amp. Okay. Now there's my website, visualphysics.org. You may have clicked on it or not. Let me just see if we can bring that up. And so manifestos, in other words, what are my outlook, what are my attitudes towards physics and whatnot. Some tutorials, animations, downloads. And in particular, I think preprints is important because what it does is this. I'm a lunchbox physicist, so I can't publish to the physics preprint server. I use this tool, and what's different about this tool is that yes, not only are there web pages and PDFs, but there's a Mathematica notebook. And what's cool about this is every paper I've gotten from the real official preprint server, it's like, how can I work with this? And it's like, I don't know. They're hard to understand. With this, you get a Mathematica notebook, and you could actually do variations with it. I mean, actually do calculations. So that's something different. Then the talks page, I just put up forums. I say my goal is to build a community, but I don't want to claim that I have a community, because you'll notice that Doug, and Doug. Okay, and that's the status of that website at this time. Okay, so if I could find, there we go. All right. So there's a lot more math on the back than words, as I've said before. So what is a Lagrange density? You know, it's one of those things. I remember when somebody said, "You've got to figure out the Lagrange density," I got scared because it sounds fancy. It sounds really hard. And the first thing that said, "Oh, this isn't so bad," was the units. It's mass per unit volume, okay? And what it turns out to be is all the ways that energy can exchange with each other inside of a lunchbox, okay? And that's it. And we're going to figure out what to do with that sort of thing, but that's all it is. And it's the properties of the Lagrangian that on this T-shirt that support every single claim. So now we move on to quaternion products. And I think everyone already knows how to use quaternions. They just use it under a different name. And that's fine. It's one of the more productive tools out there. Hypercomplex numbers are even less popular than quaternions. I think there's one guy on Comcast who uses them, but anyway. But it's basically like a quaternion product, but there's no minus signs needed. And I think that's the tool that's going to be used for gravity. So we'll see how well I can support that. So now we're going to just at least get a scan of the math to get a sense of what's going on here. So I think this is a great cosmic joke in some ways, that my unified standard model proposal is known as Laplace's equation, which means it was probably known by Laplace quite a few numbers of years ago. Okay, there's also that other equation. The first one's Laplace, but the other funny thing that happened in version 3 of the T-shirt, this is why it's good to come up with knickknacks, was that it was like, well, I know that this phi thing is dimensionless, and if I want to make that del squared thing dimensionless, well, it has units of 1 over length squared, so I need to multiply it by an area, and that's the Planck area, and that's got units of, that's a gravity, quantum mechanics, a relativity, relativist quantum mechanics. Like, oh, I was just trying to make it dimensionless. I wasn't trying to do relativistic quantum mechanics. I was just trying to make a T-shirt. So that's kind of crazy. And the other, again, I think is funny, is that this whole thing equals 0. When I did this calculation, okay, I got the 0, and I got really worried. I thought, oh no, I really messed up here. I spent a couple days going, does this make any sense at all? I kind of don't think so. And then I thought, hold on a second. With electricity, I learned a long time ago that like charges hate each other. And I learned with gravity that they always love each other. So if I really put them together, are they going to love or hate each other? It can't be both. The only rational answer is 0. It was like, whoa, that was a very happy result. At least it felt to me. So the link between them that I'll keep up here is, as far as light is concerned, it has to do with these things. This is normalizing a complex value. So this is a unit circle kind of thing. Gravity is all about these hypercomplex products going on here. The radiation has to do with the symmetry known as SU2 and the unit quaternions, and that's the way they do it in those heavy books. And the nucleus, I'm arguing that if you multiply 2 of these together and this vital star here, then it might be a way to represent that group and have that symmetry. If all these symmetries are in the Lagrangian, if each one of these A's has that, then there should be conserved charges for electricity, 3 for the weak force and 8 for the strong force. And then the no-stinking Higgs has to do with the plus and the minus here. That's it. All right, so that is a overview of the T-shirt. So now we go on to the quiz, because these sound really, really hard. I mean, are you going to be able to handle this kind of thing? And I think you all are. Okay. Well, maybe that youngster. Where's that super youngster? All right. So, do you know how to factor b squared minus c squared? Yeah, shout it out. Shout it out. All right, yeah, excellent. All right, now, can anyone calculate the following? 0? Yeah, oh, yes, all right. It's not 0. 0 would be the wrong answer. You do get a b squared and a minus b squared and e squared minus e squared, but you get cross terms. And the cross terms actually add up. Okay, there are 4 of them. Oh, I divided by 4, so it's just BE. All right? How about multiplying complex numbers? I don't even bother. Come on. That couldn't be easier. Right? All right. So, but what if I cheated? What if I cheated the world and made I squared equal to plus 1? I bet this looks really similar to the last answer, huh? Yes! There's just one sign change in there. Okay, now, what I'm using 2 scalars, t and t prime, and 2 3 vectors, r and r prime. And so I say, okay, what are all the basic combinations that I can get of that? Scalar, 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 vector, dot product, cross product. It's like, yeah, that was easy, I hope. So there they all are. We've got to do some calculus. I remember when I first approached calculus, it had the lead time of everybody saying, calculus is the hardest thing you will ever do. If you can do calculus, you are smart, And then you learn these 2, and it was like, are you kidding me? That's easy. These 2 are, at least, like y and 2x. And it turns out that this is all I'm going to use in the Euler-Lagrange equation to derive the Maxwell equations. Going back. Now, it's going to look a lot more complicated. There's going to be a lot of detail, okay? But just wanted to give you a heads up. All right. So, and then we need to find the minimum value of something. So this is one of those things where you take the derivative and set it equals 0 and go, oh, it's just 0. Okay. And now we have to know a little bit of physics. Electric field in the E direction is just this minus these 2 things negative. So that's it's the time derivative of A minus the, derivative of the scalar field in the X direction. The B field, this again is, all you have to, this one always takes me a little bit of time. Which one is negative, I suppose you all have your own tricks. The other thing is, there should be no thing in there that has an X in it. So it's got the AY, it's got the AZ, it's got DZ, it's got a DY. And that's the quiz. So I hope you didn't find that very difficult. And so here we go. This is what I attached to the email. So just a review of it. What we're going to do is merge complex numbers with scalars and vectors to create quaternions. So this is the links between complex numbers, scalars, and vectors. And in this case, that R that's in yellow, that's really a single number. Whereas the R with the arrow is a triplet of numbers. And you'll notice that, hey, there's a TT prime, there's basically a dot product. There is a scalars kind of being expanded by vectors, that sort of thing. But there is no cross product in the complex number. Okay, so basically, quaternions formalize that link between these two, and they provide a minus on that dot product. And that's about it. So hopefully that doesn't seem that unfamiliar. But if we had the I squared equal to +1, then it's like that one, except there are no minus signs to remember. And I call this thing, I have to generate my own symbol. This is not like universally accepted over the globe. In fact, I don't know anybody else who does it. But I'm calling that the symmetric curve. So you don't have to remember the sign. Oh, I love that. It's nice when the math makes it nicer, easier to do. All right, so that was it for merging complex numbers with vectors and making quaternions. Now we're going to do what I call third grade math, but it's really an introduction to graph theory. Okay, so let's see. Hello. All right. Oh, it went back. Kind of that mode. All right. So in third grade, we learned how to add, subtract, multiply, and divide. And we also learned, maybe you did the speed tests with that. I remember doing, like, trying to do 100 problems in 3 minutes. And we actually loved clay and pipe cleaners. So I'm going to combine the two. And this is, that clay ball there is a vertex in graph theory speak. The pipe cleaner is an edge. And we knew back in third grade that 1 times 1 equals 1. This is an unidirectional graph, if you want to get fancy. But I think you could have taught third graders about complex numbers with these pipe cleaners. Okay, so we still have 1 times 1 equals 1, and 1 times I equals I. Okay, I times 1 equals I. The only tricky thing is that I times minus I brings you back to 1. And so you have to go back on an edge that's different from the edge that brought you out. Okay? And so that is graph theory. And hypercomplex numbers are easier to make out of clay and pipe cleaners. You just drop an edge. Because it doesn't matter whether you go there or back. 1 times I is I, and I times 1, and I times I is 1. That's how you get back. So that vertex is labeled with an I. So that's easy. And this is what a quaternion looks like. It's got an I, a J, and a K. It's got 3 complex numbers. The complex numbers always emanate out from that black ball. That's the real number over there. The reason cross products are confusing is the colored plane. Okay, that's where you have to remember which way you're going in order to get the sign correct or not. Okay, and the reason I like hypercomplex numbers is they're like quaternions, only quite a bit simpler. I mean, it's actually easier to build this. Okay, I have this in my basement. No signs to remember, just simplify things all over. Now, okay, so. The summary is that the quaternions and hypercomplex products really, to me, look like we're covering all kinds of ways to combine collections of 4 numbers together. And the reason that this is actually so important to me that I brought it up to you folks is because as you go, if you go into theoretical physics, you'll find people like one type of number, or they believe they can do all kinds of things in another kind of way. And, you're not going to change their opinion, really. They've got a commitment to that kind of way. And there are not that many people with a commitment to quaternions, and even fewer who care about hypercomplex numbers. So I have to say, why am I grounded in the possibilities? And it really gets down to this graph theory, feeling like that's got to be such a systematic, thorough way of exploring what four numbers can do with each other. It's got the look. It doesn't have the formal, I can explain it to a math head, why this is better than some other thing, but it appeals to the third grader in me, really. Okay, so now we go on to the next section. We go from we go from third grade to the hardest, perhaps the hardest section. little transition. So we're going to derive the Euler-Lagrange equation. And what that's done, that's what gets you from the back of the t-shirt to the front of the t-shirt. And in some ways I can't do this. I can only give you a sense of what it is. Don't try and say, yes, I totally get every single detail that's going on there. All right. So I have to explain what an action is. An action integrates the Lagrange density, that mass per volume, over space and time. Okay? And so the result is mass times time. And you go, okay, so I do this for a second, or I do it for a million years. I bet I get really different numbers. Why are you bothering me with this? It's not the action that matters. It's the variation on the action that matters. What I'm going to try and do is find something in here that I can change, and if I integrate over a second, that variation I did doesn't matter over that second. If I look over a million years, that variation doesn't matter. Okay? And this is actually minimization problem, as we had on the quiz. Okay, just a little bit more complicated. So let me give you three important cases here. If the Lagrange density is not a function of time, that means that energy is conserved. And I don't know, this seems like I'm getting deeper into, how nature works. Before I was like, yes, energy is conserved. But now it's like, well, I bet there's a Lagrangian in there, and I bet whatever the Lagrangian is, it doesn't have time in there. There's no e to the minus t that you might have if something was exponentially decaying, something like that. All right? If the Lagrange density is not a function of space, if it doesn't matter exactly, if there isn't a place to put the x, y, and z, then actually it means that space is a symmetry, and it means that momentum is conserved. And the third thing is, if you look at that Lagrange density and it's not a function of angle, then you're going to get angular momentum conservation. All right, so if we have a Lagrange density that depends not on space, not on speed, not on these things, but on a four potential A, and it also depends on derivatives of that four potential A, we're going to vary these things, and we're going to find minimum. And that is at the heart of the Euler-Lagrange equation. So here again we see we've got a Lagrangian, we're doing variations on that sort of thing, we're integrating over space and time, and we're saying, okay, let's get a minimum out of that variation. Okay, so this is my sketch of how to derive it. You start with that Lagrange density that's really only a function of A and the derivatives of A. You form an action, which means you add it all up, and you vary that action. You vary that action with respect to A and the changing fields of A. But this gives you a problem. The problem is, let me see if I can do it back here. The problem is that this is an apple and that's an orange. So how are you going to deal with the apple and oranges thing? And the way you deal with that is you use the product rule. And this looks a little crazy, because I think it is a little crazy. But that step 4 and 5 are where if you're in graduate school, you get rock solid on how that all works. Okay, so I'm a little hand wavy here, but I think you get the product rule saying if I take this del on both of these things, I get just that acting on there. But there's a theorem of Gauss that says that this whole thing is actually equal to 0, and that can be the case only if those two happen to equal each other. And now we go, well, here we've got the difference, the variation on the fields, and here we've got variation on the. That's like the other one. So why don't I just plug this into that equation that was on the previous slide, and if I do that, I end up here, and it's all a variation on the field A. Okay, so that's good, because then I can say, well, if I really want 0, let's make sure that thing is 0. Okay, and that is Euler-Lagrange right there. Okay, so that's to give you a sense of it. Don't feel like you can go and do a proof of it, but that's kind of a sense of it. And then if you say, look, show me the details. Okay, this is what it is. If you were to write this all out, people are going to think you're brilliant, because it has so many partial differential equations. Okay, so along this side we're doing, these aren't so bad. It's d phi, dax, day, daz. This looks like a nightmare until you go, well, there are patterns here too. Okay, that top line is all phis, then all ax's, then all ay's, then all az's. Okay. Sorry, these guys. And then you notice that you get pairs. But you get a lot of them. And that's the nature of the game. So that is what we're going to use to derive the Maxwell equations. Once we have something to put into the Lagrangian. And that brings us to this. We can all agree on Lorentz invariance, even if we haven't taken special relativity. But special relativity is, in essence, it deals with Lorentz invariance most of the time. Okay, so the Egyptians figured out something we can all agree on. That 3 squared plus 4 squared equals 5 squared. They used that with the rope thing so many years ago. It was useful math. I don't actually know whether the Egyptians figured out they can do the third dimension or not, but it's not that big a step out there. And it was Einstein in 1905 who modernized it and said if he was in a rocket ship going by here, the lengths would change, the times would change between measurements, but this thing is called an interval. If you calculated that, everyone would agree to that number. So all it is time squared minus, x squared, y squared, z squared. And that's called the Lorentz invariant interval. Okay. So if you were now moving like a crazy man all over the place, you could do this as long as you could figure out what the functions were of that crazy motion you were doing, that f and the h, and that's this kind of thing that general relativity allows you to do. As I say, only a few special cases, and I'm not going to force any on you in this over these 3 days. That is too hard. Okay, so that Lagrange density, that mass per unit volume, requires a Lorentz invariant numerator. And what you do with Quaternions anyway is you just multiply it out and go, oh yes, that's the dot product, and it's got to have that minus because it's kind of like a complex number. And then otherwise it's scalar times a vector, and the cross product. So that's it. And what's amazing is that first term of any quaternion product is a Lorentz invariant scalar. And it is the reason I purchased Quaternions.com in 1997. I was in the library and I saw, oh, actually it wasn't this particular one. It was t squared minus x squared minus y squared minus z squared right in the page, and I said, that's not luck. And I was so struck by that after taking a good course on special relativity and knowing how important the Lorentz invariant interval is that I bought it. And this actually, current coupling term actually is on the t-shirt on the back. All right. So the hyper-complex products that I talked about, you can actually make something that's Lorentz invariant as long as you add a conjugate operator in there. And now because Lorentz invariants are so important, I basically kind of team them up. I never take one of those products without also taking a conjugate. And this also appears on the t-shirt. Okay, so that's 2 out of the 4 terms actually on the t-shirt. It's this one and it's this one, but I had to somehow come up with the other 2. And I was struggling to figure out how I could teach this, and I realized all I have to do is mess it up. Remember, all you have to do is multiply 2 quaternions, you get a Lorentz invariant interval out. Well, what if I put a conjugate there? I messed it up. Is this bad news? I'm going to argue that eventually we'll see it's actually good news. Okay, so I get this scalar that's definitely not Lorentz invariant. It's got the plus sign and a bunch of other things, 3 vectors. Actually, well, anyway. So that scalar is such a problem. What are you going to do with a broken scalar? You throw it away. And so that's all you do right there. Take this thing, take its conjugate, and it goes away. So now what I have to do is make a Lorentz invariant scalar out of that. And that's kind of gets more tricky. But there are two types of 3 vectors inside there. There's the axial and the polar one. And the polar one has the property that if you change the order of it, you flip signs. So let's try and be complete in our analysis. This is always my thing. Let's be complete. Let's be complete with our multiplication. Let's be complete with looking at both sides of our cross product. So dA gives me one thing, and then if I flip around the signs, did I mess that up? I always worry about messing up my signs. All right. I guess I did it right. I was saying, why is that plus? Because that was minus, so that's good. All right. So these 2 3 vectors, they point in different directions, okay? But the thing is that their norms will be the same. So if I calculate the size of these 2 norms, if I take one vector that's pointing this way, and another vector pointing that way, and I say, what are your norms? Now subtract those, I'll get 0. So that will work out. And so that's the idea, is 0 must be a Lorentz invariant interval. And you get this really, really nasty, complicated 3 vector, and I'm pleased to tell you guys that at least at this point, we don't have to analyze that. That would be scary. Okay, 0 is comfortable. I like 0. And in fact, this is going to be the key to the homogeneous equations. That, amazingly enough, is the B dot E sort of thing. And then, I don't know how to really prove this in a pithy way at this point. All I can say is at this point that if you take the 2 orderings and you form the product of that, then that gives you a Lorentz invariant. And that's actually going to be this b squared minus e squared thing that's going to go into the Maxwell source equations. So I think we're getting done with that one, which is good. So now we're going to actually derive some of Maxwell equations. Oh, and it's going to take a while. But hey, Max's work. All right. So, the basic strategy of deriving the homogeneous equations is to plug a Lorentz invariant into the Euler-Lagrange equations and go. So what are the Maxwell equations? This is my big picture, step back, what is it all about? And so it defines how a current density is the source of all changes in spacetime, of four spacetime potential. Okay? Four particles that are traveling at the speed of light using Quaternion multiplication. So this is really just like, I'm just being thorough. I'm not skipping anything whatsoever. What's completely odd, and no one else on the planet's going to say at this point, is this link to Quaternions. Okay, and believe me, you can do this all without mentioning the word Quaternions, which is usually the way it's done. Okay, so I'm going to construct a complete set of first-order changes in the potential. And how am I going to do this completeness? I'm just going to multiply this out. That's it. Okay. So, and I can see that 3 vector there is negative the E field and the B field that we talked about so long ago on the quiz. We had that on the quiz. But let me just repeat this, okay? The most basic complete Quaternion derivative is electromagnetism. It's like, I couldn't have made this up. You know, I just don't think that's luck. It's not luck rearing its head here. All right, so, but that extra scalar field is a problem. It's a problem because it won't turn, it's not actually the Lorentz invariant. Okay, and if you're in physics grad school, you can probably say why that gauge field must be 0 so that things can travel at the speed of light. I certainly know of those arguments. I'm going to just say this is one of those times when I'm going to be a little hand wave, okay? And I'm going to say you can't have scalar gauge terms in your Lagrangian and travel at the speed of light. And what do I mean by that more in a concrete way? Because I'm a lunchbox guy. You can't have a dv dt, you can't have dAx dx, you can't have dy dy, you can't have dAz dz. And you'll notice that the thing about this guy, it doesn't have dphi dt. It isn't there. And there's this funkiness going on here when you look at it up close about i's, j's, and k's. And you figure out that I was just being crafty. I didn't want to write the ai, the xi. I wanted this to be invariant under gauge transformation if I want to sound very formal, which I usually don't. Okay, so we need an invariant. So we do what we worked out before, which was to say, I want to square that, one of those guys, subtract the square of that thing. What am I going to get out of this? And this is that square of the things where one's a plus and the other one's a minus. And you basically get out E dot B out of that process. Okay. So we're going to now derive the no-monopoles law. And we're going to start with one easy term, EX. Okay? Then we're going to pair that with a BX, multiply that out, clone a bunch of lines. Actually, I should say we're going to Sudoku. I think I'll change it. Sudoku a bunch of lines and look for the resulting patterns. Okay. So we've got to write out every single term of E dot B. And it was scary. It is scary. When I was writing up these notes, it's like, how am I going to do this? Okay, I am going to start out easy. I'm going to write out EX. And I remember, oh, it's got a bunch of X's. Everything's negative. And it's like, okay, it's got to be kind of like. And then it's got boson. All right? And a bunch of other terms that I'm not worrying about. I take the first step. This first step is simple. All right, so BX is everything not in EX. So it's got AY's in there, it's got AZ's in there, and it's got the other two derivatives, and the only tricky thing is remembering the signs, and you go, oh, I first make contact with AY and then AZ, and so then that flows out. All right? And you multiply this out. Okay? We've done this many times back in 8th grade or 9th grade sort of thing. And when you do that, half of the terms are positive and half are negative, which is kind of nice because we know if this really is going to make it to the no-monopoles law, we want a whole bunch of cancellations going on. Another cool thing to just see about it is like, it's like every one of the 4 directions makes a contribution. So there's a thing from time in that first one. There's a thing AX, there's an AY, there's an AZ. The phi thing is like the time guy. And it's got an X, it's got a Y, it's got a Z. It's like we are all sharing. Isn't this beautiful? Okay. And so now what we do is we clone EX to make EY and EZ. So we haven't filled this stuff in because it'd be scary to write it all down at once. Okay? But it's not scary to write EY or EZ. Okay? Particularly when we line them up and go, oh, I can fill that in straight away. Now what do I do? Well, why don't I look for some patterns? And it's like, oh, yeah, I see 2 Z's, I see 2 Y's. It's like, that's very much like curl. Okay? So what if I kind of like play what I call curl Sudoku? And this is actually formally curl Sudoku. This isn't like approximately. All right? That second line there, we know, since it's the Y, it's got to involve a dx and a dz. And if we play Sudoku, I can't put the dz here. I have to put dz here. That means I have to put dx there. And this final thing has got a dx and a dy. And formally, it is, again, Sudoku. I can't put y's there. It would be wrong. I had to put y's here. I had to put x's there. I never thought, until I gave this talk, that Sudoku had a practical purpose. But here we are deriving the no-monopoles law, and that's curl Sudoku. Okay, we played it on that line. Guess what? I've got y's and I've got z's. I'm going to play the game again. And when I play the game again, I go, oh, my z and x. Oh, yeah, z had to be there. That puts x over there. And then this was ay had to go over there, forcing ax right over there. And I think this is pretty. All right, this is our Lagrange density. Just take a step back again. This is Lagrange density. This is every way that energy can be exchanged inside of a volume involving B and B. And you notice that the E field is sitting right next to the B field. And all we have to do is take that, put it in the Euler-Lagrange, and we'll get the result. But people just aren't good at dealing with this much stuff. Actually, there are some people who are good at this sort of thing, and they scare us. Okay, so I had to make things much simpler than that, and it's much simpler to do things one at a time. Make them simple. Okay, so the first one is we're taking derivatives with respect to phi. And then we notice we've got this, all we have are phis. There's no ax, no ay, no az. And then we've got these pairs of derivative things going on. Okay, so let's look at our Lagrange density that we have, this E dot B thing. And, oh good, I get to ignore half the terms. I always like when I get to ignore half the stuff that's there. That's very good. But what am I going to do with the calculus going on there? Well, remember the quiz. We had, what's the derivative of xy over x? It's just y. But what if x is this complicated d phi dx? Well, it's just that complicated d phi dx. I mean, it's just a different way of writing x. And so if we end up with one of these things like that, we're going to, and then take the x derivative, we're just going to get the second derivative, and it's going to be a mixed derivative. So you can see, maybe I should have gotten that. But, you see, we've got these two, and they end up over there. And the phi goes away, and we just end up with a 2 over there. So it's not even hard to write down what the mixed derivatives are. Okay? So let's go back here and say, okay, so I can see I'm going to get an xy all the way up there on the top. I guess I can't do gesture too well, that's right. And then I'm going to get the same thing down here. It's just that they've got a different sign. And if you spend some quality time there, you go, okay, one's a zy, the other's a yz. You can see there's this changing of order, but that doesn't matter. What matters is that they got different signs. These guys are all going to cancel. All right? You already knew that, kind of suspected as much. But what's cool is that if you now look at them line by line and say, what is that line? That line is, they've got an extra, they both have a dx in them. So if you pull the dx out, you go, oh, that's one of those B fields. So I'm basically taking the repeat for all of these things. I'm taking the divergence of the B field. And so that is how to derive the law. This is kind of a graphic which will give you a kind of more sophisticated appreciation of the no-monopoles law. Because the cancellations happen across lines. But the del dot B, that's across the line. So, so that's kind of an interesting visualization. We're now going to try and derive Faraday's law from the same darn Lagrangian. Okay? I'm not going to change it out on you. I'm just going to use different parts. What parts am I going to use? I'm going to look for everybody who has an AX. And it turns out, again, it's half the terms. But, let's see, yeah, half the terms. And you can see the red arrows show, oh, if I start taking, I'm going to get mixed derivatives here. I'm going to get a ty guy. I'm going to get a ty there, a minus and a plus. Oh, I'm going to get a tz up there. Oh, so you can kind of see cancellations going on between the plus terms and the minus terms. What's harder to see maybe is this take the curl of an E field, and I don't think this slide really summarizes that too well. I'm sorry about that, but that's, so that anyway leads to Faraday's law, and you get the cancellations. All right, let me see what I'm doing. All right, so this I call the forgotten way to derive the homogeneous equations. Because usually what they say is it's a vector identity. We'll give you a real simple explanation of how to do this, and you're done. And believe me, that is faster and easier than what I've just done. And you can use the tools of differential geometry to say this also in a very sophisticated way. And so nobody puts E dot B to much use. But I wanted to be, in essence, logically consistent. In other words, I'm always using Lagrangian because that's how energy can be changed in volume, and then I do this Euler-Lagrange to get out what I want. All right. So we're going to derive more. All right, more field equations, and we're always going to do the same darn thing. Okay. So I'm sorry if I get a little repetitive. Writing out the Lagrangian, writing out the terms of the Lagrangian, applying Euler-Lagrange. Take all the derivatives, collect them together, and then we'll have our statement. But we've done two, okay? We've got halfway. You're halfway home as far as Maxwell is concerned. So we will move on to derive the Maxwell source equations. Okay, so there we go. Again, we got to plug something into the Lorentz invariant into the Euler-Lagrange. Now this time we're going to do this b squared minus e squared. Now in essence, just to say, well, what is new and different about what you're doing? Only this first step is, okay, where I say I'm just going to take these guys and just multiply them together using math you knew in high school to get b squared minus d squared. Yes, I get something called the pointing vector, which shows up in EM. I get it for free, okay? It's like, people give a big, long explanation. It's like, no, just multiply it out. It's there. Nature uses it, okay, because you multiply this stuff out. So, but if I was in a more formal class, they would write out, they would write it this way, just to shop and compare. They write something like this. I would have to explain, actually, I'm pretty sure I couldn't do this to high school students, unless they were in detention for a long time. This ends up there, okay? But I'd had to explain a covariant and contravariant tensor. I'd had to explain, we'd had to do some tricky note keeping to realize what happens when you reverse those together. I'd have to do the same down when they're written down below, and then I'd have to show you how to crunch all that stuff together. I've done that. That's the way it's taught in Jackson, and that's the way they teach it to everybody else. And I think it's just computationally difficult. That's easy. Okay, so I like easy. All right, but from here on out, though, we're doing standard stuff. Okay, there's you can take this home. All right, and not shock anybody. So we write out the E and B fields. We multiply them out, and then we Sudoku for the rest of them. So we write these guys out, square them up, and we get all these terms here, and we notice who's positive. Well, the only positive guys are the B field guys squared. Everybody else is negative. That's fine. And so here's a case where we're cloning now. Now, these are the B fields, and that's the E fields. And, okay, so these guys are all minus. Oh yeah, that's right, they have the same sign. They should all be the same. And this guy, he's the B field, and he has some sign mixing going on, so he's got different signs. And since it was B squared, that makes sense. All these signs make sense. And really, it's just a game of Sudoku. Okay, so, but the Lagrange density is a little different. There are two small but important changes. One is we throw a factor of about half in there. Because if you take the derivative of B squared, you're going to get a 2 down there, and we don't like that 2. We're just going to get rid of it by throwing the half in front there. And then we need a current coupling term. This is the JA sort of thing. And I'm writing those as quaternions, and all we need for this thing is the scalar. And I should say, I do research, so I think, well, what could I explore if I had infinite resources? It's like, well, the vector of that seems perfectly fine object. I bet if you did the vector of that, it would mean something. I think it would mean something that was really difficult. So I haven't waded into those waters yet. But what's cool is quaternions give you a place to go. It's like the vector, that should be important too. All right. So, but I'm not going there because I don't need to derive the Maxwell equations. So that's the picture of it, and we see we've got our B's on one side, we've got our E's on the other. And that is our Lagrange density. That's every way that energy interacts in a volume. So here again, we're going to start easy. We're just going to start on phi, and all we have to do is pay attention to the tail end of that. Everything else we can ignore. Which makes sense, right? Because B fields don't have any phi in them anywhere. So we can't use any of the B, and it turns out that out of the 3 terms, only those last 2 matter. So we got 1 current coupling term and 6 derivatives. Sorry. Oh, I hit the wrong button. Bad button. All right, so there we are. Sorry. 1 current coupling, yes. All right, so now we start doing the taking calculus, and it's like, oh, we got the mixed term thing in here again, okay, but we also have squares, and the squares just kind of bring us back. So we just get this the x's. So all the square terms are really easy, and all the mixed terms, well, they're not that difficult either. At least it could be far worse. Okay, so when we go ahead and do this, we take the derivative with respect to phi, and that gives us rho. It's like, oh, another easy bit of calculus. And here we go, oh, we get that mixed term sort of thing, and we get one of these pure terms, and a mixed term, pure term, mixed term, pure term. So, okay, that's pretty good. And you go, oh, that is Gauss. We got Gauss. We got Gauss, and that is good. Okay. All right, now for Ampere's law, again, we're using the same Lagrange density. We're just using different terms in there, which is really cool. Okay, so it's all and you notice I picked out everybody who's got an AX. And it's a situation where there are just two. There are just two. There are just two. Okay? But you go, oh, this crosses the great divide between what's on the beast having to do with B, what's having to do with A. And so when I was thinking about, well, how do I explain which one is which? You know, it's like this has got this shifty thing going on. I bet that's a curl. Okay? That's kind of the way I get it visually, that's really occurring. Can you crank through and go, okay, that is a time derivative of the E field. I think that one's pretty easy, the time derivative of the E field. This one I think you simply have to memorize, okay, or maybe figure out something cuter than I am, because who knows the curl of something, okay? You've got to be pretty hardcore to know that. You could believe that's the curl of something. And it turns out to be minus the curl of of A. But that's something you just have to crank or I don't know. So anyway, so this is the EX. We're taking the curl of B, and we're taking the time derivative of E, and so that is Ampere's law right there. And so Gauss is only about the E field, and Ampere is really about both of these things. And this is my trying to summarize all four in a graphical way. We've got our two Lagrangians on top. We've got the E dot B, so B and E are sitting right next to each other, or they're nicely separated. Okay? And then we have to go through the Euler-Lagrange mechanics, where when we got these identities, we saw the cancellations happening across the lines. And then we had Gauss's law, which was only E field, and Ampere's law, which was curl of B and the time derivative of E somehow being the current. So that's it. You now know how to get to the Maxwell equations, all four of them, in a formally precise way. So that's very good. At least I hope you feel it's good. I hope you aren't going to hunt me down afterwards. All right, so now I'm going to derive my own work, okay? I claim this is a gravity equation, and I'm using exactly the same technique as before. As far as I can tell, very few people think this is true, but that's not because, it's because I haven't been able to reach them, or a bunch of social reasons. But anyway, let's see how similar it is to before. So we're going to construct a complete set of first-order changes of a potential, okay? But this time I'm going to use that hyper-complex product. And you'll notice that I'm using these yellows here and there. It's like, why? Because I'm really using exactly the same slides, okay? I said I don't want to work too much. I'm using the exact slides, and I'm figuring out where the signs change. And what's amazing is that exactly half the signs are going to change. Well, actually, this part is exactly the same. And that's actually the key element to why the Higgs, we might not need the Higgs. But in here, with an E field, I had 6 minus signs. This time, I've only got 3 minus signs. And with this symmetric curl, that means they're all got the same signs. With the B field, they used to have half, right? Half positive, half negative. So it is, I think there's like 24 terms, exactly 12 of them change. It's like, wow, that would be very convenient if it worked out. So, again, the most complete hypercomplex derivatives, is that connected to gravity? That is my hypothesis, and we'll see whether I can support it in the next 50 minutes or so. So I call these, since they're so darn similar, I just call it small e and small b. Small b is easier to remember because it all has the same signs. And small e is a little trickier in that the A term is the one that flips signs. Okay, so again, we got to get rid of that gauge field, okay? And that way, our gravitons can travel at the speed of light for reasons that grad students would understand. And this is going to be a recurring technique. There's going to be no one of those scalar terms. All those scalar terms would belong in that 0 spot. They aren't there. This stuff is traveling at the speed of light. So that's good. Okay, so we need an invariant. So what should we do? Hey, why don't we get another one of these b squared things? The difference of 2 squares. And e is positive this time around. And again, there's a perfectly valid 3 vector out there that I'm not going to work with. It scares me. Okay. So what's our plan to derive it? Same as before. Okay. Slide looks similar. We're going to write out these 2 terms. We're going to multiply it out, and we're going to clone. And so we write it out. A few signs change. And what's kind of funny about this is that the only terms that don't change are the mixed terms. Everybody, the pure guys, they all flip their signs. It's like that. What that means, we'll find out. So we get to write out our thing, and we get to use the same slide again, and we just say, your pure term, flip your sign, flip your sign, flip your sign, flip your sign. That's very simple. And all my mixed terms, they stay the same. And so I put in my factor of a half, and put in my current coupling, and so now I said my Lagrange density is complete. I feel good, warm inside. And so now I'm going to apply Euler-Lagrange. I'm going to pick out my phi terms. Oh, those are the guys all the way over on that side. And I'm going to go ahead and crank this through. I'm going to say, what's my calculus of derivatives? And it's like, oh, that was pretty easy before. It's pretty easy again. And then I get this rho equals whatever. And end up with a summary statement that looks like this. But actually, let me go back here, because I don't think I commented this anywhere, which is kind of too bad. It's like, we go, back in high school, we learned about Newton's potential theory. That is Newton's potential theory, okay? Sorry, it's not. It's more. These 3 terms make up Newton's potential theory. And the deep critique that Einstein even realized, as soon as he came up with special relativity, he was thinking about gravity, right? And the problem was, he said, the problem with Newton's potential theory is if you change the potential, that charge density at all, it has to go everywhere instantaneously, and that breaks my special relativity rule. And people who are scary bright, Feynman, Weinberg, they know how to go literally from Newton's law to Einstein's theory of general relativity, his field equations. I can't follow that, okay? I could just bow in respect for people who can do that. What's cool about this expression is it doesn't have that problem. See, because there are terms that depend on time. So I can be far more hopeful that this is going to be consistent with special relativity, particularly since I've used 4 vectors throughout. I've never not written a 4 vector. So, and there's not that obvious flaw about changing in time that the rho will lead to something changing instantaneously. All right. So now we go into an Ampere's law sort of thing, and we focus on an AX term, and we see we've got this splits things going on. But here's the beauty of symmetric curls. It's like they don't hurt our heads as much. Minus, 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 minus. Oh, I bet that's the symmetric curl of an A, which it turns out to be. Well, there's the details for the AX and our summary thing, saying yes, that is the curl of B, and that is an EX because we've got, and you just have to worry about did I get the signs right, sort of thing, exercise. All right, so that's Ampere's law for gravity. Looks awfully darn similar. So Gauss is only about the small e. Ampere is about both. So that, in my opinion, is how to derive equations that are related to gravity. And that is not what this shirt is about. This shirt is about more than that, amazingly enough. Okay, so what it is... Oh, actually, let's deal with the homogeneous gravity equations. Again, the same technique, except that's not Lorentz invariant. So what am I going to do? I'm going to go, oh, this doesn't work. Those guys aren't going to cancel. I guess I don't know everything about my own equations. And that's really the bottom line. I don't want to belabor the point. I'm hoping, it's like, that's what research is like. I dream of this. I dream of somehow taking a symmetric thingy and ending up with a zero there. When I find that day, if that day ever comes about, I think I might be able to get to homogeneous equations. But I'm not there. So it's just not there. And that's the bottom line for the homogeneous. So it's half-baked or partially baked. All right, so now we're going to try and derive the unified field equations. Those are the equations on your shirt. And you're probably getting used to my story. I'm going to plug a Lorentz invariant or Lagrange equations. Okay? So, I'm going to construct a complete set of first-order potential changes, but I'm going to use both products. I'm going to use both Quaternions, and I'm going to use hyper-complex numbers. Okay? And, but this time, I've got that G field, and I'm not going to subtract it away. Oh, actually I am, but in a moment. Okay? See if I just crank these things out, this has got both orders, and what I do up there is I do funky things with where exactly I put the conjugates. That's when you're dealing with hyper-complex numbers, that's how you kind of do the same thing as changing the order is with Quaternions. So I get a G field, what I call a G field here, small e, small b, and G over here. Now, that G guys, those guys are problems for traveling at the speed of light, so why don't I subtract them away? Okay? And this is, in fact, what is written on the back of the t-shirt. Okay? So I'm doing this all to get rid of those G things. But, well, not quite, right? I mean, if you just think about the EM part, which would be right over here, that does depend on G, okay? So that means that does apply to particles that don't go the speed of light, like myself, okay? Then this stuff in here, if my claim about it being related to gravity, well, that actually is not gauge invariant, which means that it applies to particles that don't travel at the speed of light. But because I subtract one from the other, overall, it is invariant under gauge transformation. Okay, and that is in essence the magic that goes on with the Higgs mechanism. But what they do instead is they say, I've got all these symmetries, great, and what I'm going to say is my vacuum is a false vacuum, and I spontaneously symmetry break, and that way I don't mess up my symmetries, okay? This to me seems, I have no false vacuum. I'm a man without a false vacuum, without a false God. And to me that really feels good. I like that. All right. So we're going to derive things very similar. We're going to start out by writing Euler-Lagrange, the Lagrangian. And the thing is that the mixed terms were the same. I pointed that out. And the reason is that I'm going to subtract one from the other, and so I'm going to wipe them out. Wipe out those mixed terms. Give me purity. Now, here's another reason why, I don't mind betting the house that this isn't right. Because you look at that and you go, that's beautiful. It's only the square terms, okay? It's only the square terms. I'm getting rid of the Higgs, despite what we were trying to do at LHC. I don't know. I'm willing to bet the house. So we're going to work on the phi terms, and you go, hey, there's only one column of those. This is getting easier, isn't it? Because, oh, and by the way, the reason, look, we used to, for Maxwell, we had one current coupling term, 6 derivatives. We narrowed it down to 0 coupling terms, and 3 derivative terms. Like, that rocks. And so there we go. Laplace. Okay. And so that's, yeah, I think that's right. It's just add those two fields together, take the divergence, and that's it. So now we do Ampere, and Ampere is easier to deal with. Okay, there's just 3 terms that have to be taken derivatives of. That's what's on the front of the t-shirt. That's the other one. Okay, so that's kind of nice. Yeah, and I think I figured this out, and to be that whole. No, that can't be right. Can it? No, it's not right. That value is to a scalar, and this is about a vector. So, burn your notes. I think it's a time derivative. Actually, is what it is. Okay. So Gauss is only about E plus E, and Ampere is about both. All right. So where do we go from here? We've got the field equations, and we got it the good old-fashioned way of plugging things into Euler-Lagrange. We only have 3 more sections to go. Okay, so I'm going to give you a sense of group theory. I can't give it all to you. And I'm throwing in the word multiplication. Why? Because I know multiplication. Okay? Since 3rd grade. All right? Group multiplication theory, that's found in the standard model and on the t-shirt. So I'm not going to cover the entire subject, just what's needed for the t-shirt. And the basic theory was known so many years ago. You know there's an identity element. You know there are inverses. And you know there's associativity. This time, those 2 equals those 2 times this, whatever. There is one new idea, and that is the idea of closure. That is, if A and B are in a group you have defined, then so is AB, the result. Okay? Group theory can get really hard quickly because they have lots of letters, they have lots of numbers, they have lots of relationships between all these letters and numbers, and if you're in grad school, you get really good at all those kinds of numbers and relationships and whatnot. All right. So the standard model actually uses 3 continuous multiplication groups. It's called U1, SU2, and SU3. Here's this example of how they mix numbers and letters together. That is the covariant derivative for the standard model. Do I know how to use this for any practical calculation? Not the slightest idea. Okay? It gets really scary pretty quickly when you start to work with that. But the important thing that we can take from this is that if you have a symmetry, then you have a conserved charge. And how many terms that are in each one of those determines how many charges you have. For this Y thing, that happens to be U1, there happens to be like one thing that can generate it, there happens to be one charge, it's called electric charge. For the weak force, there are 3 things. And there are 3 weak field charges, and that's what that one is. And for the strong force, there are 8. And so there are 8 charges. Okay, so let me show you what the U1 group is all about. It's basically complex numbers with a normal 1. And so if you just write a circle in the complex plane, you got it. That's got a nice simple visual, okay? It's got a normal equal to 1. And this is about electric charge conservation. And it's if that was a complex valued function, or thingy, whatever it was, you divide it by its norm, and that's always going to be on that unit circle. Now, you said that's a complex number, but I'm dealing with quaternions. Quaternions are simply 3 complex numbers. They share the same real. They just, instead of pointing in one direction, they point in 3-dimensional space. But I really think of them as being very similar. But the group SU2 is actually called a unit quaternion. And so these basically, it's a unit sphere in space-time, is the way I think about it. And you actually need 3 numbers to generate this group. And if you go, but why is that? That's when you start to get into graduate school group theory about why it really is 3. It's not hard math. I think it's n squared minus 1. But they can talk about that for a while as it lies. So, but then it's 3 charges are conserved: W plus, W minus, and Z. Okay, and then there's this group called electroweak, and that has 4 things, and it's U1 process U2. So I said, well, if I'm using Quaternions, why don't I just multiply them together? And because a Quaternion has 4 degrees of freedom, it seemed like a thoroughly reasonable thing to do. And well, I think this is a reasonable thing to do. I haven't broached this subject with somebody who is a group theory professional, so who knows whether they would attack me violently or not for suggesting this to you. Actually, it would probably get more violent about this one. Because then I also noticed that 4 plus 4 equals 8. Okay, I get very sophisticated in my math. And it turns out that the group SU3 has 8 generators to its Lie algebra, if you want to be formal. And so I thought, well, why not just use 2 of these? And the reason is group theory. Because if that really represents SU2, U1 cross SU2, then you get the same thing out of it. It stays in the group. That's the whole point of group theory. So I was actually stuck here for, I don't know, year and a half. I work on this time scale. It's like, I don't have to get this done in a week. I can wait a year. I can let something bother me, piss me off for a year. I got so quickly to U1, SU2, U1 cross SU2. It's like, how am I going to reach out and grab hold of SU3? Because if I don't, I want to make this clear. I knew that if I don't get to SU3, I don't have it. I've got 2/3 of the standard model, doesn't cut it. All right, so my realization was, oh, what if I put a conjugate there? Then it's formally, you would say, its multiplication table is different. And so it makes a different group. But that thing, because norms multiply together, they stay the same. That's got a normal 1. That's got a normal 1. Everybody got a normal 1 on the table. I clearly have 8 choices I can make. Put whatever the heck values you want. You take the norm of that sucker, it's going to be 1. I can guarantee it. And again, I have yet to see this in the literature, but it's almost comic, the results of this. Because if you look on a Wikipedia and they say, we're going to show you how to represent SU2, you really want to hide under a couch if you see the details. Because you're not going to be able to go home and remember it, There's a square root of 3 here, and the 2 is over here, and the minus is over here. Mine work out to be plus 1, plus I, plus j, and plus k, minus 1, minus I, minus j, minus k. I can remember that. Those are the 8 generators of my group, my way of representing this group. Okay, that's the way you would. It's closer to how people would formally say it. I'm not formally trained, so I'm probably not quite saying that right, but it's something pretty close to that. Okay, so the biggest positives, actually, and I consider this from a philosophical point of view, enormous. Okay, there is this, the group theory, standard model has been around since the 1960s. They say it involves these 3 groups. And the honest ones will tell you, we don't know 2 reasons, the 2 things about this. Why it's limited to 3, and why it's these 3 in particular. This is one of the reasons that physicists don't crow about the standard model. They're a little bit embarrassed by its success. Okay, I feel like I can answer that, both questions, and it's all about the symmetries of 1 in 4-dimensional spacetime. Because if this thing, if I put alpha over here, if alpha and beta happen to be equal to each other, that's what I get out. And so it's trying to think about this in a group multiplication way that leads to these symmetries being in this Lagrangian, being in this symmetries in this Lagrangian, means there's conservation of those charges in the Lagrangian, means there's going to be electricity or weak field, strong field. Okay? So what are the weaknesses? Oh, the weaknesses are scary. That I haven't solved a single problem with this as a proposal somehow being connected to the weak force. I mean, and that's just huge, okay? I have not solved a single thing. I don't even know how to approach a problem with a strong force, okay? There will be people that just say this is far, far too simplistic, okay? Because some of the most detailed and impressive calculations done in all of mathematical physics are done with the standard model, and how you think you're going to connect that to reality is like a dream sort of thing. But it's something I can work on, and so that's why I just wanted to make sure there were big warning signs here about that sort of thing. All right, good. So we have to deal with spin. We are going to try to be able to spot spin 1 and spin 2 in a Lagrange density at the high school student level. Okay? So, spin 1 particles, whatever that means, okay, have this property that like charges repel. And spin 2 properties have properties that like charges attract. So the first one is great for EM, the second one is great for gravity. I can't, in a simple way, explain why that's the case. I can point to the book, Feynman Lecture on Gravitation, that's where it was made, and I accept this. I'm not going to fight this one, sort of thing. They talk about doing calculations about scattering and, sort of thing. I didn't go through the details. I don't understand. But I accept it. And so both of those types of properties are required for a unified field theory. Okay? So we're going to use quantum mechanical angular momentum projection operators. No, we better not, because that's too advanced, that's too fancy. All this stuff, amazingly enough, can be done without the jargon. And the key is that book by Feynman. And I spent, I think, 3 months reading like about 8 pages. I don't read fast. It's that I'm trying to figure out what's going on at my kind of level. And I finally saw, or we saw on page 39, he's writing x plus or minus ix, x plus or minus iy. It's like, oh, that's complex multiplication. You just do that, and you end up with this xx minus yy plus or minus 2x, 2ixy, whatever. That was on page 39. And then I went back. You see why I had to spend so much time. It's hard to read backwards. Back on page 34, and basically he's doing x plus or minus yi, x minus plus yi. That's all he was doing in terms of the algebra. So that took a while to see. And so if I write this out using conjugate operators, something kind of funky happens. There's, I guess I hit different terms on the top one, and here I put them both on the same side. Seems like an odd little thing to do. But something really important. You see those zeros? Did I not have that slide? Or did I get confused? Yeah. Oh, yeah. Well, I didn't explain this important property. The zeros on the end. That's what's important. Okay. To make a spin projection operator without using words, all I want to do is get a 0 at the end. Okay. 0, I understand. Spin projection operators don't get scared. Okay. So if I look at just the imaginary parts of this thing, then I notice that I get, if I were to add those two together, they cancel. If I were to add these two together, they'd wipe each other out. Okay? That's how I'm going to get my 0. I know how to get to 0. Okay? And then, this is a step that I'm even a little fuzzy about. He's thinking about these in terms of, well, these guys kind of add up together, and it ends up being like a 2 theta I. And this one's is like a 2 plus I. And of course, if you add those two, you multiply those together, right? You multiply those together, you'll wipe them out. So the spin 1 stuff is the top line, and I guess that's a really lousy color to choose. But that's spin 2 down there. That's how you do it with complex numbers. All right. And I like and thinking about this. Feynman was a magician, and he works out in the open. But he was multiplying 2 currents together. The currents, if you go closely through this part section of the book, he's using 4 vectors everywhere. Well, you can't multiply 4 vectors together. Okay, you're not supposed to do that, but he does that. And when he now switches over to complex numbers, he's putting the jx term, he's treating that as a real number, and the jy is imaginary. And it's like, and why is it pointing in the z direction when he gets through? It's like, I think he's right. I think he's getting the right results, but my accountant kind of person is saying, I think he's cheating. No, wrong word. I think he's doing magic. Okay? He is a skilled magician. He's really amazing fellow. I think most people all probably would agree. With Quaternions, none of these things are real. They're all the imaginary components. Okay? And I'm going to do the same thing with hypercomplex things. And I'm just going to crank it through, and I'm going to get all the same darn terms. But they're going to be kind of where they should be, as it were. And these things end up at z because those are the rules. There's no me guessing sort of thing. So what I'm hoping is that the spin 1 is going to be this j times a thing, and the spin 2 will be the hypercomplex product. And so like charges repel, which is nice for EM, which is about spin 1, which is about curl, and like charges attract, and nice for gravity, that's spin 2, and that, I think, is a result of a symmetric curl. Yes, so that is, hopefully gives you a sense a little bit more about the issue of spin, which normally is pretty darn hard to approach. So now we go on to the final one, the final section of slides, yay! Okay, we're going to try and find a static solution for the static Gauss's field equations. Okay, so the standard derivatives that you do in the high school, they just assume you're dealing with a flat piece of paper. It's like, well, what if somebody rolled up that piece of paper? It's like, I wouldn't talk to them again. No, but the covariant derivatives can actually deal with curved space and curved space-time. But things get hard, okay? Let's not kid ourselves. I think that the standard model basically says, hey, if you want to curve your space-time, that's fine with me. Just tell me what you did. This is called fixing the metric. And I'll proceed. Same thing happens with string theory. It says, look, just tell me what your metric is, and I'll go ahead. Well, what general relativity says is, well, no, it's always curved, and I can figure out, I can calculate in only very few cases how is it exactly curved. What I'm going to try and hope with my G-field work is that I can do it both ways. I can do it either way. Okay. So the G-field solution in flat space-time, Laplacian sort of thing, that was unknown to the 17th century now. And I am just pointing this out because it's kind of fun, particularly for freshmen who are going to be told the wrong answer. And they get the math right, but the physics is not. You really need to put that one up there. And you say, well, every single problem that they're going to ever assign to me, they're going to take the derivative of that. That one's going to go away. Why are you bothering me? It's because we're showing respect for Maxwell in a certain way. What happened was, everybody who made super huge contributions, they contributed to light and to gravity, right? Newton did that to contributions to gravity and to light. Einstein certainly did. And Maxwell only made a contribution to how light works. What was his problem? Okay? And his problem, what he realized was that if he thought about electricity, how electric fields work, and he thought about how magnetic fields work, and energy conservation would work, he couldn't make them be consistent as far as the signs are concerned. And we know there's a fringe element that says, oh, we got to throw in a minus mass, whatever. They were actually talking about this thing that bothered Maxwell. And I highly recommend this URL for a kind of more detailed explanation of it. But Maxwell said, I could add a huge number up in front of it and make sure that's positive. I really want to do that. I just have absolutely no reason to do so. Okay? And it turns out that along comes Einstein. Then Minkowski says, here's a solution. And then they say the Taylor series is none other than that one, where effectively we're throwing a huge honking positive number. When I say huge honking, it's because if you calculate that for the Earth, what is it, 10 to the minus 10 or something like that? Anyway, whatever, why don't we say it's a super small number? It's a super small minus number. That's what bothered Maxwell. He didn't want to put a positive constant that was 10 orders of magnitude bigger in front of it. He should have. He would have been right. But, and that will spell it out for you. But I bet nobody's going to throw that one in because they all know we're going to take the derivative, and so it doesn't matter. It matters to make a consistent story between EM field theory and gravity field theory. Okay, so we're going to try to get to a GEM solution. Actually, no, I take that back. GEM is the word I use for the unified field equations, and this is really a G field solution in curved spacetime. Okay, so covariant derivatives, they involve the normal derivative. Oh, thank goodness. And they also have this Greek letter. That's the scary part. Okay, so that has things in it for group theory. It has things for dealing with curved spacetime. And what you can do is think about, what if my potential A was really boring? Like you take the derivative, you get nothing out of it. Then it would all be about the connection. And my first field equation, that rho thing, would be basically be taking the divergence of this connection. Okay, and I've actually seen it taught in a book, in one of these gravity books. It's like, don't take the divergence of a connection because it doesn't transform like a tensor. Well, that's right. I mean, it's not wrong. But if you have a really boring potential, then it's an okay thing to do. So you just have to add an additional stipulation. So what is that gamma? Well, actually, there's not an answer. There's a whole field of study, many different areas of study about what you should use. And it is hard to understand. And I'm going to use Christoffel symbols of the second kind, because that's what Einstein used for general relativity. Well, what does that fancy bit of math say? Well, it's basically, if you've got a metric, you start taking derivatives of these. And there's ones that depend on space, there are ones that depend on time, there are ones that depend on off-diagonal elements, something I haven't gone into. But guess what? Lunchbox Physicist makes things easy. So I'm going to work with static and diagonal, so I only have to worry about space-dependent derivatives. Those are the only ones that matter. Okay? And so, and I'm going to make it further easy. Am I a lazy man or what? Well, maybe not with this many slides. Okay, I'm going to use this exponential metric. And if I do that, then what happens is you, well, if you take a derivative of this thing with respect to space, you get that thing back, right? And you take the derivative of the exponent, so you got that. And it's another vital detail that this Christoffel symbol also multiplies this by the inverse of that component. Well, the inverse of an exponential times the exponential, that wipes it out. It goes away. Okay? And so you go, oh, then I just want, oh, that's familiar. That should be familiar. the derivative of what is that? The Laplacian operator of charge over r. Okay, so the thing is that this exponential metric does not solve the Einstein field equations. And so I am in conflict with general relativity. I'm saying it's the classic way you talk about this, about in the science world. It's like general relativity is a wonderful theory. It has had a very long and productive life, and I got something better. That's my hope. How close am I to general relativity? Okay, what you do is you take a solution of general relativity known as the Schwarzschild solution, and then you do a Taylor series expansion, and then you compare the terms. And here again, you can't see any of those terms in green, but that's okay because they're the same. Okay, there's not any bit of difference in the green terms between what I'm proposing and what's there for the Schwarzschild. The thing is that when they say we've tested general relativity in the weak field, they mean they've tested exactly those 5 terms and no others. Okay? So if those 5 terms are the same, we are totally in agreement. We only get into disagreement when we get into these yellow things. Okay? And so who's right? Well, we haven't gone there. So I would. The reason I bet on my stuff is I'm more familiar with it. Okay, but being more symmetric is a better thing. My proposal is more symmetric. Exponentials, I like to say, are the calling card of a correct theory. It's like anytime you get really deep into stuff, they start sprouting. And why do they sprout like that? A good reason. It's because they basically, when the exponential is super small, you get unity. Nothing happens. When your effect is super small, you better make sure nothing happens. Exponentials are good. Now, when you start something happening, you get some kind of oscillations going on, vibrations going on. That's what exponentials do. When you think about the sun going around the Earth, that doesn't happen. Earth goes around the sun. It's done this, what, 4 billion times? Now, if I did this 4 billion times, would you say this looks like a simple harmonic oscillator? I won't do that. But it's got that sense of, this is an exponential at work, okay? And my proposal actually predicts 15% more bending than it does than general relativity. And so why haven't they done this? Okay, because we know they did the experiment back in, 1919, and they had to fudge the data a little bit, but subsequent tests, they showed that, yeah, Newton said it was supposed to do this much, 0.75 arc seconds, and Newton said it was, Einstein said it was twice that. And it was confirmed, it's rock solid. So now we just have to get to the next level. How many spots over do you have to go? Okay, this is obscure knowledge, I know. You have to go over 1,000,000-fold to get to those other terms. We've gone over 10,000, which is good, okay? We really are rock solid saying those first 5 terms, they're the same. It would take, hundreds of millions of dollars and dedicated folks to go after those final terms, and then they're only 15% different. And then people can say, well, there's a quadrupole moment in the sun, and that would be about the same size as your effect. So it's good on a philosophical level that they're different. It's frustrating that it's so subtle that I don't think I'm going to hear about the experiments done anytime soon. So here's the final slide. This is a comic strip provided by Lowell, who's a grad student in South Korea. No? All right, anyway, it goes, what is this? And on the chalkboard apparently is the back of the t-shirt. It's a new unified field theory I'm working on that disses the need for the Higgs boson. Looks like a real gem? Thanks. Doug misspelled forward is dog. And he's basically doing a riff on me because I thought Doug being misspelled backwards is God. But, Said, well, you know, you misspell your name bad enough, you can really spell anything. So, yeah, that's a deep insight. So anyway, that concludes day one on deriving the Maxwell equations and more.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
I always wanted to do a lecture hall with a microphone like this, you know? All right, so seriously, so what does it take to do creative physics? And I think it's pretty clear. You really have to have a flexible mind. You really have to challenge who you are to yourself, okay? And you can challenge, you know, who you are, like in the kitchen. You can check out, you know, in social situations. I better not go there, okay? But you know what I mean. And I think you also need to be like really flexible in like a physical kind of way, okay? How flexible are you? Okay, so I'm going to really challenge myself. I'm going to try and take my foot and see if I can put it behind my head. Because if I could do that, okay, I'd be a really flexible guy, right? And I could have, you know, what I need to do theoretical physics. Okay, so I actually am going to have to remove my hand. Can I even touch my feet? Okay, there. I'm pretty sure that Hawking can't do this, okay? Was that cool? I'm not sure. Okay. I wasn't able to get there in a long time, but thank you very much.